delta y0, and the limits are from 0 to 1. And on applying the limits, we'll get each times, on putting p1, we get y0. From here we get 1 by 2 del y0. So the result can be further simplified if I take out 1 by 2 as a common factor. So the result inside will take the form like this. Okay. And now within the bracket, there is a difference operator involved. We can use the definition of the forward difference operator, and we can replace it in the form of 2y0 plus y1 minus y0. So ultimately we get h by 2 times, on simplifying this will give you y0 plus y1. So this is the result we obtain within the domain from x0 to x1. If I show it here, this is your whole length of the interval, and we take start from x0 and moves to the point x1. Still we have to reach to xn. So similarly, now we are going to generalize it. Instead of using the first interval, we'll be generalizing it for the whole domain on proceeding the same lines. So here we are going to extend this formula for the whole domain. You have to keep this result in your mind. You keep it on the board so that I could use it. Now for the whole domain of the integral from x0 to xn, for the function fx dx, we can split the integral into the sub-intervals x1 fx dx. The second can go from x1 to x2 fx dx plus x2 to x3 fx dx, and you can write down many more integrals, and the last will be xn minus 1 to xn fx dx. So here I have used the property of the integrals and split it up into the subintervals, and each interval is of length 1. You can see from x0 to x1, x1 to x2 and so on. Now I will be using this result. For this result, we have derived this one, so I can replace it, the result with this. Here we can write down h by 2 times y0 plus y1. Similarly, if you proceed on the same line for this integral from x1 to x2, so the result will be y1 plus y2. And if you keep on doing, the next result will be for the third integral will be h by 2, y2 plus y3, and many more integrals you can write down. And for the last integral, we get h by 2. Inside there will be xn minus 1 and this is yn minus 1 plus yn. So here we have replaced all the integrals with the simple algebraic results form. Out of these n integrals, intervals, we can take out h by 2 as a common factor. And further, if you look at it carefully, you will come to know, except the first term and the last term, all the terms inside or in between are appearing twicely. So we can write them as a multiple of 2. So here let me erase it and simplify the final result for the trapezoidal rule in the form of h by 2. Inside I am taking the first term as it is, and all the terms in between them are multiples of 2. So we can write down y1, y2 and so on up to yn minus 1, and the last term as it is. So this becomes your first formula and is known as the trapezoidal rule. And here we have just given the construction of this formula. Now we are going to construct the second formula, which is named as the Simpson's one-third rule. In order to construct the Simpson, now you have to keep this formula in your mind. I'm going to erase it and constructing the second formula for the Simpson's one-third rule. Simpson's one-third rule. For this formula, you have to truncate the series. In the previous case, we have truncated it up to this order. Now you have to truncate it to the second order. Okay, truncating to second difference. Okay, truncating to delta 2y0 and taking the limit from 0 to 2. So here we are going to write this integral in the form x0 to x2 fx dx each times py0 plus p square by 2 delta y0 plus 1 by 2 p cube by 3 p square by 2 and delta 2y0, and the limits you have to use from 0 to 2. So after applying this restriction on this polynomial, we got this result. Now if you apply this limit within the bracket, we get h inside 2 times y0 plus 4 by 2 gives you 2 delta y0 plus 1 by 2, it gives you 8 by 3 minus 2 and delta 2 y0. So on applying the limit, we get this result. Now if you simplify this, 8 by 3 minus 2 gives you 2 by 3, and 2 can be dropped down with this outside 2, so the net result is equals to 1 by 3. So I am replacing this by 1 by 3. Okay. Now, if I take this as an LCM or as a common factor, so this takes the form h by 3 6y0 plus 6 delta y0 plus delta 2y0. After doing this, now we have to replace these differences, and this is the first order difference, forward difference, and this is the second order forward difference, and now we are going to replace them with the polynomials, polynomial function, algebraic functions, in other words. So let me create some space to write here. I'll be taking start from here, okay? Okay, after doing this, now if you keep on writing it as it is, inside there is 6y0 and plus 6, and the forward difference definition gives you y1 minus y0 plus delta 2 y2 whenever you apply it wisely. So this gives you y2 minus 2y1 plus y0. So this is the expanded form of the difference operators, and we have just replaced these difference operators by the algebraic formations, and next you have to simplify them. So this it can be written as h by 3 6y0 plus 6y1 6y0 y2 2y1 and y0. If you correct the like terms, so here these are, this can be dropped down, we have y0, and next is minus 2 times y1 and sorry, this is 4 times y1 and plus y2. So this is the ultimate result we obtain whenever we have used the integral from x0 to x2